the rules of quantum mechanics truly capable of describing the world we see and touch every day? This fundamental question has fascinated physicists for decades, and the answer could shake up how we understand nature itself. Most people assume that the bizarre behaviors of quantum mechanics, particles acting as waves or existing in two places at once, are reserved for the strange world of atoms and electrons. On the other hand, your coffee mug or car seems to obey straightforward classical physics with no weirdness in sight. But here's where it gets controversial. What exactly separates quantum reality from the ordinary, everyday world? Are we missing something crucial? A group of scientists from ETH Zurich in Switzerland and the Institute of Photonic Sciences in Barcelona, Spain, has taken a remarkable leap forward in this mystery. They've managed to extend the quantum wave properties to objects thousands of times larger than single atoms, silica nanoparticles about 100 nanometers across. This is a massive step closer to bridging the gap between the microscopic and macroscopic realms, and it could open doors to new kinds of quantum sensors, especially for measuring gravitational forces with unprecedented sensitivity. The team started with these silica nanoparticles, carefully trapping and suspending them in a vacuum using a tightly focused laser. Think of this laser like invisible tweezers holding the particles perfectly steady. These nanoparticles naturally scatter the laser light, and interestingly, the way the light scatters can tell you exactly where the nanoparticle is. The phase of each photon carries this positional info. Using a clever loop of measurements and feedback, the team applied electric fields to cool the particles down, close to their quantum ground state. In simple terms, a cooler state means the particle's quantum features become purer and more pronounced. The particle begins to exhibit more of its wave-like nature. At first, they measured a coherence length, a measure of how far these quantum waves stretch, of just 21 picometers. That's 21 trillionths of a meter. And this is the part most people miss. Boosting that coherence length isn't as simple as flipping a switch. To coax the nanoparticles, quantum waves to stretch even further, the scientists manipulated the laser's power. With high energy, the nanoparticles sit tightly in a sort of optical bowl. Imagine a marble snuggled at the bottom of a steep valley. By cleverly lowering the laser strength in 2 precise pulses, the bowl becomes shallower, and the marble gets to roll further. That is, the particle's quantum coherence length grows. In their experiment, this extended the coherence length to 73 picometers, more than 3 times the original value. But here's a controversial twist. Preserving quantum information is extremely tricky. Rossi, the lead researcher, points out that every time the nanoparticle interacts with its surroundings, be it stray light, air molecules, or anything else, some quantum information gets lost in the chaos. This process is called decoherence, and it forces the once quantum-acting particle to behave like an ordinary, predictable object. The team had to act fast and carefully pinpoint every source of decoherence, with light scattering as the main troublemaker. They minimized this during their expansion pulses, when laser power was low, helping them stay ahead of the decoherence race. But even after all this, the quantum coherence length is still far tinier than the particle itself, 73 picometers versus a 100 nanometer diameter. Is there a fundamental barrier that prevents us from seeing quantum effects in big objects? Rossi himself isn't convinced there is, noting that achieving quantum coherence on the nanometer scale should be possible in principle. The next challenge will be applying even more expansion pulses, or using new types of traps combining both light and electric fields. Interestingly, electric traps might sidestep some of the decoherence that comes with optical methods. And this brings us to the final hook, the debate that could stir up any classroom or comment section. What do you think? Does our everyday experience hide underlying quantum strangeness we have yet to measure? Or is there a deep law that sets quantum and classical worlds apart forever? Could future technology give us quantum behaviors in even larger visible objects? Dive into the comments. Do you agree with this research, or do you think there's a limit we might never cross?